in the visual programming Facebook group lately, an interesting library which has nothing to do with visual programming on first sight was brought to my attention: Thi.ng. At first, the minimalistic, clean look and feel of the imagery presented on the website caught my eye, but I was also a little bit anxious because the whole project is written in Clojure and I'm by no means at all an expert in that language. Frankly, I hardly know the basics. But ignorance should never keep you from exploring, and I know an interesting library when I see one. So I started dabbling around and was immediately stumped because I seemingly couldn't get it to work on my machine. Clojure runs on the Java virtual machine and uses a build tool called Thi.ng, and I ran into one version conflict after another. Then I realized there is one go-to tool to use when you need a defined, known-to-work environment to run your software in: Docker. So I'd like to share the process of how I got Thi.ng to work and generate simple yet beautiful graphics with you. In a sense, this episode is 50-50 a hands-on Docker workshop and an introduction to the language and library. I'm a beginner in myself, but I will do my best to share my learnings with you. To start out, let's look at what Thi.ng's geom project README tells us. Thi.ng is written in a literate programming style, which means that source code is intertwined with description and documentation in one document, and in order to use it, we must extract the code first. Here this process is called tangling. So let's see how we can get a working draft up and running. First we go to hub.docker.com and search for a Clojure image, which we, not surprisingly, find. Afterwards we can immediately jump in by starting a container based on this image. If you try this the first time, you will need to sign up for the Docker Hub, but it's well worth it. So we specify that we'd like to start a container with an interactive terminal, -ti, that will be deleted after closing, --rm, and run a bash shell on it. Easy enough. The process of downloading and extracting can take a few minutes depending on your setup. We then continue to do some basic setup on our Debian-based container. We update the apt cache and install Git and Emacs, which will be both needed to obtain the source code. Once we have done that, we can clone the repository and start the tangling process. What's more, we need to install all modules into local jars so we can use them later on. Let's head to the SVG examples directory and fire up a line REPL. We load an example file that downloads and renders Blender's Suzanne model. So it seems as if something was rendered. We just don't have the chance to see it because we have no way of accessing it from outside the container. Let's change it now. Let's now go to this process again, but this time formalize it in a Docker file so we can store and tag the image. As usual, we start with a from clause to specify our source image and then sequentially run the commands we just did manually. We can now build the image specified and tag it locally as Thi.ng. I'll speed this part up. It's basically the same we just did. It's just going to be baked in an image this time. And here we got it. The important message is at the bottom. Successfully tagged Thi.ng:latest. We can now Docker run a container based on that image. This time we just add a bind mount, the -v option, from a local directory, which doesn't need to exist, it will be created, to the temp rendered folder in the container. Let's head to our examples again and load the Suzanne demo. We exit the REPL, copy the generated SVG to our temp rendered folder, and exit the container too. We open the directory on the host and see the SVG version of Suzanne has been created. Now we get to a point where the use of Docker gets really interesting. We can run services in Docker, such as a database, or attach to shells as we just did, but we don't need to. Docker containers can also be used to run a single command on some source code. Let's therefore rework our Docker file. We actually don't need all the tangling and installing if we just use Docker to manage a Clojure project that we store on our host. We specify user source app as our work directory, since that's how it's specified in the images documentation. And then we specify two related directives, entry point and command. They are very similar, the differences between them are very subtle, but let's just say that in our case, entry point specifies the command that is run by Docker every time this container is run, and command is the arguments or actions we pass to it. There are cases when you don't need an entry point, for example, but here we can make good use of it. We specify the entry point as line, the lining and build tool, and command as a chained action of do, deps, and REPL, which will load the project dependencies and start the REPL one after the other. The key point is that you can override the command, but not the entry point when you run the container. We rebuild and retag our image and do the following. We run our container with a bind mount pointing to a Thi.ng folder in our host's working directory and say new app lcg-viz at the end. As mentioned above, Docker will expand this to line new app lcg-viz and, well, create a new app skeleton for us here in the Thi.ng folder. We open our editor and see the project structure. First, we are going to make some changes to the project CLG definition file, especially adding the Thi.ng dependency, which will then be downloaded automatically from clojars.org. So I wondered what would make a good little starting project here, and an old project of Patrick's came to my mind, which dealt with the linear congruential generator, which most of you know as a pseudo-random number generator in most programming languages. It is defined recursively like so. Now, just looking at this, you see that every next number depends on the current number with some math applied and then a modular division afterwards, usually by a very large number. You can look up the Wikipedia entry for examples. What this means is that the sequence of numbers generated by this algorithm is in fact periodic, because if we ever reach the same x of n again and all other parameters remain unchanged, it has to start all over again because of the modulus. And it turns out that you can visualize this if you take tuples of successive generated numbers and plot them in their respective 2D, 3D, and so on space. You get what is called hyperplanes, and it's very easy to visualize them. So let's paste in some code, and I'll go over it very quickly just to give you a hint of what's going on. It won't be very deep because, one, I don't know enough about Clojure and the Thi.ng framework. I barely got my feet wet myself, so please bear with me here. Two, this episode is meant to give you a hint about what it's like creating applications with Docker, and three, because we're over time here already. So at the bottom here, we see that an SVG file is spit out by a function named lcg-svg-2d, which obviously takes some of the LCG parameters and an iteration count. We are going to look at what this function is composed of now. At the top we have the LCG function itself, which spits out the next pseudorandom based on the passed-in arguments. Nothing surprising here. Next is the LCG sequence function, which additionally receives a start value and an iteration count. This function loops until an accumulator array has the specified length, and on each recursion conjoins the current accumulator with the next LCG value and passes it to the loop again. That's what recur does. Next is the lcg-svg-2d function, which does nothing more than make dots from such a sequence. We start with a sequence, partition it in pairs, and make a circle with a random bluish color. That's all what this map function does. So out of it we get an array of SVG circles, which can be passed to SVG group, which will effectively capture them together in a G tag and give it some background. Eventually this is piped into svg-doc, which just assembles an SVG document and serializes it to be written to a file afterwards. Let's try that out real quick in our container. And there is our output, some two-dimensional LCG hyperplanes, vulgar lines. Now, maybe just a few quick thoughts what I find interesting about this approach. Its declarative nature. If you compare it to other popular frameworks, you can almost say the code is the graphics. Because it's pure in the functional sense, you can insert or skip transformations at will and see what comes out. When you've gained enough experience with the framework and the language, I can imagine you can almost see the patterns that emerge, especially when they are of iterative or recursive nature. In other programming environments, this is the point where the code almost always becomes procedural and/or imperative. I don't know enough of this framework yet to say what's possible and what's not, but as of now it at least serves as an opportunity to create interesting material to use somewhere else. Let's try and explore that in a future episode.